Hello, pre-calculus students, and welcome to our continuing lesson here on complex zeros of polynomials. And in this video, we're going to take a look at dealing with actually some higher order polynomials here, whereas in the last video, we only dealt with quadratics. And if you've been watching all the videos and you've been following this in Mr. Wen's class, this is the same thing as the example from section 2.4. So after we finish this, you might want to look at that again because this is very much related. Okay. So it says here, x plus 4 is a factor of f of x. Find all the other factors of f of x. And to do that, remember, finding all the other factors, we're going to use polynomial, or sometimes, if it's possible, synthetic division. Okay. Look back in the notes and see if synthetic division is applicable in this case. This has a coefficient of 1 and a power of 1, so it is applicable. So now we can do this synthetic division, write down the coefficients here, 7, 24, negative 15, 4. Okay, I'm going to go a little bit quick here. If you have a hard time with synthetic division, look back at some of the previous videos. Bring down the 7, this gives me negative 28, negative 4, multiplied by negative 4 gives me 16. 1, negative 4, and a remainder of 0. So now I know that f of x is equal to x plus 4 times 7x squared minus 4x plus 1. And I've designed this just so that all these problems are connected. You can see that this term right here and this problem that we did in the previous video are exactly the same. And we know the zeros is 2 plus or minus the square root of 3i divided by 7. So one of the things that we can do is, we would normally have to, factor again using some method, quadratic formula, or completing the square. Okay. But we've already done that here. So we know that these are the zeros. So we know this function has 3 zeros. Negative 4, because x plus 4 is a 0. 2 plus square root of 3i over 7. And 2 minus square root of 3i over 7. So we can write this in factored form. This way. And it's not going to be pretty, but it'll work. So f of x equals x plus 4 times x minus this term times x minus this term. Okay. And there you have it. This is the factored form. Again, it is not very pretty. It's not neat, but it works, and it is the correct solution. Okay. And so at this point, you're probably thinking, why do we do this? Why do we bother to do this? Well, there are some applications to imaginary and complex numbers, but more importantly, a lot of what we do with graphing, a lot of what we do with finding zeros and determining if zeros exist at all rely heavily on complex numbers existing. Okay, we only know that this can be factored all the way down if we have complex numbers available to us to work with. Okay. And if this number cannot be factored down completely, we're not really sure about all of the solutions to this problem. We wonder if negative 4 is the only solution. Maybe there's other solution, other parts in the graph that we don't know about. It's only when we can write it in a complete factored form that we know we've exhausted all possibilities. There is one real solution and two complex solutions to this problem. So we're going to end this video here. This is, again, a kind of building on what we had before, and building on this idea that for any higher order polynomial, we can write it, we can break it all the way down into its somewhat simplest, or more technically, the factored form. And all of these factors together, when we multiply them out, gives you this real function right here.